Hi everyone, welcome back to the second part of the video on section 12.1. Now we're going to introduce our three-dimensional coordinate system, or our rectangular coordinate system in space. So the idea is we want to describe the position of a point in space. The way we're going to do that is we're going to have some fixed frame of reference. And that is going to consist of three coordinate axes. So we're used to looking at two coordinate axes. Now we're going to throw a third one in the mix as well, and this one's going to be in the third direction, so we're thinking of this as sort of coming out of the page. We'll call these x, y, and z. And so then a given point in space, let's call that point P, is going to be described by three values. The values are going to be a value A, a value B, and a value C. What are of these values? These are essentially the directed distances of this point P from the various coordinate planes. So for example, C, the last component, is the distance this point is from the xy plane. So I'll drop a vertical line down from our point. We'll see where does that vertical line hit the xy plane. It hits it at some point there. And so the C value is this distance that point P is from the xy plane. I'm going to draw a few more lines of reference into this diagram. So we'll draw a horizontal line coming across, sort of thinking of, I'm trying to draw like a rectangular box here. I'm sort of thinking of this as the front of the rectangular box. And then we've got these line segments going out in these directions. And there we go. Okay, so there's our point P. Maybe I'll put P in a different color. So our point P. Now, what is A? A will be the distance from the YZ plane. So basically, the A value is the x coordinate of the point. What is the x coordinate? It's the distance to the YZ plane. So that would be essentially this distance there, or that distance there, since this is a rectangular box. And what is B? B would be the distance this point is from the XZ plane. So that's this distance here. And then we've already drawn C. That was the first one I indicated there. That's the height of the point. So we've got C is the height of the point, A is how far it's coming out of the page or into the page if it's negative, and B is how far to the left or right of the XZ plane this point is. Now, when I put that point down first, it was hard to tell. Where is it? Is it out front? Is it behind? You know, just by way of contrast, let's draw the same set of coordinate axes, and I'll put another point. Maybe I'll put a point Q. It's hard to tell where this point Q is. You may say, well, no, it doesn't look like it's hard to tell where it is. Well, as soon as I start throwing lines in here, you're going to see that maybe it's a little bit difficult to see where it is, because this one, if I throw some reference lines in there, oh, that's actually sitting with a negative x value. It's sitting behind the YZ plane. And we'll throw a few more reference lines in. And so there's our rectangular box. And so this is a point where the x value is negative, the y value is positive, and the z value is positive. Where it's almost look exactly like where I drew the point P, but with these extra reference lines, that helps us figure out where it is in space. And this is going to be important when we're drawing points. Having these reference lines in place is going to help us figure out where, in fact, they actually are, because what we're trying to do is we're trying to draw a three-dimensional object, you know, the coordinate axes and the point, in a plane on a piece of paper. And so giving us some extra lines of reference are going to be very useful. Okay, so this is all I want to introduce in this section, is just the idea of how to characterize a point in space. So we'll just review some terminology. In our diagram above, I said we started with three coordinate axes. In fact, even before we had the three coordinate axes, we probably should have started with a point in space that those three coordinate axes all pass through. That would be our point O, and that's what we call the origin. So the origin is a fixed point in space. You just fix it however you want. It's your point of reference. What are your coordinate axes? These are three mutually perpendicular axes. So three mutually perpendicular axes that pass through the origin, that pass through O. What do I mean by mutually perpendicular? I mean any one of them is perpendicular to any other one of them. So they're all perpendicular to each other. What else do we have? So there's our three mutually perpendicular axes. Again, we're drawing the x coming out of the page, the y off to the right, and the z going up. That's typically how we're going to draw our axes. Now, it may not be. We may draw our axes in another way. So for example, if I drew my x-axis going this way and my y-axis going up, which is typical in Calculus 1 and 2. Now I want to fit the z-axis in there. Well, we've got some choices to make. Do I do the z-axis going in like this? Or do I do the z-axis coming out of the page? There's a question about that third axis, which is the positive direction for it. We know what its direction is, but what would be the positive direction? Because the direction would be this line segment that's mutually perpendicular to both x and y axes. But then which side of it is considered the positive axis, and which side is the negative axis? Well, that's where the right-hand rule comes into play. The right-hand rule tells us that if we know the direction of any two of the axes, then we can get the direction of the third one. In particular, it tells us that if we have the direction of the x-axis and the direction of the y-axis, then I can get the direction of the z-axis by taking my right hand, so this is my right hand, you point your finger in the direction of the x-axis, so that would be, this finger here, imagine just pointing it in the direction of the x-axis, and then curl your fingers in the direction of the positive y-axis, and your thumb is going to point in the direction of the z-axis. So if I do that for this picture over here with the x and the y already shown, I take my right hand, point my finger in the direction of the x-axis, curl my fingers in the direction of the y-axis, and then my thumb is now pointing in the direction of the z-axis. And since it's my right hand, my thumb will be pointing out of the page, and so I know that's the direction of the z-axis. So this right-hand rule allows us to get the orientation of the axes correct. So x direction, y direction, and then the corresponding z direction. So in other words, what looked like a freedom of choice for a direction on the third axis, the right-hand rule is imposing a particular choice. Of the two directions, which will we take to be a positive direction for that third axis? We take the one that's consistent with the right-hand rule. Okay, so there's our three coordinate axes. What they do is they create any pair of them, a plane. So these are the three coordinate planes, the xz plane, the yz plane, and the xy plane. Those planes split the space up into 8 regions called octants, and the octants are described by where the x, y, and z values are positive or negative. So when all the x, y, and z values are positive, that's the first octant, and so that's this one sitting out front here. And then if we sort of go around in a counterclockwise fashion, so if I move to the back, that's where the x value is negative, but the y and z values are positive. And then I can keep moving around. This is where the x value is negative and the y value is negative, but the z value is positive, and so on. All 8 octants are described in this way in terms of the signs of the x, y, and z values. So that brings us to the coordinates. We've sort of briefly used the idea of a coordinate in talking about the signs of the points. What are the coordinates of a point? So a point P in space, in 3 dimensions, is described by 3 numbers. What are those 3 numbers? So we usually refer to them as A, B, C, or X, Y, Z. What are those 3 numbers? So A is the directed distance from the YZ plane to the point P. So again, look back up at our original diagram we drew. So we've got our point P there in yellow. What I'm looking at is how far is this point P from the YZ plane? Well, here's our YZ plane. Maybe I'll sketch it in here. There's our YZ plane. This is a portion of the box in the YZ plane, but the YZ plane is really this infinite plane that has this rectangle in it. And what's the distance the point P is from that plane? It's this distance here. And that's what we call the A value, or the X coordinate of that point. And similarly, the B is the distance to the XZ plane, and C is the distance to the XY plane. So those are what coordinates are. A is the directed distance from the YZ plane to P. B is the directed distance from, so these are just ditto marks, meaning just repeat the word that's above, down below here. B is the directed distance from the XZ plane to P. And C is the directed distance from the XY plane to P. And by directed distance, I mean there's a direction associated with this. So if we are, let's go back to our picture. So if, like in the diagram off to the left, or off to the right here, we have our point Q. If I look at what is the distance from Q to the, let's say, the YZ plane. So the YZ plane would be the plane made up of that axis and that axis. And I look at my point Q. The distance to the plane made up of those axes is given by the length of that line segment there. But this is on the opposite side of the YZ plane than the positive part of the x-axis. So this would be a negative distance. Well, I wouldn't say negative distance. We're referring to directed distance, so this would have a negative coordinate. The distance to the YZ plane is whatever the length of that yellow line segment is, and the coordinate of that point, the x-coordinate of that point, is therefore negative that distance. So that's what we refer to as the directed distance. There's a distance, and it's associated with some direction. Are you on the positive side or the negative side of that coordinate plane? How about projection? Well, we can redraw our picture down here. We'll redraw that picture of, we've got our point, and we had this rectangular box that allowed us to figure out where the point is. Okay, so there's our rectangular box. And what the projection is for this point P is basically the shadow that it casts on each of the coordinate planes. So we've got x, y, z. So when we push it back onto the, let's do the x, y plane first. So I'll imagine projecting down here. So looking at the shadow it casts, if I shine a light along the z-axis or right above that point and I shine it down in the z direction, then there's the shadow it casts. This is what we call the projection in the xy plane. So if P had components A, B, and C, then all we have to do to find the projection in the xy plane is just zero out the z component. So this would be a, b, and 0. And similarly, we could project in the xz plane, so that would be 0 out the y component, so that would be a, 0, and c. And that's the projection in the xz plane. And then we could project also in the yz plane, and that would be 0 at the x component, so that would be 0 bc. And that's the projection in the yz plane. And lastly, bringing all of this together, we've got the three-dimensional rectangular coordinate system. So what that is, it's the idea that any point in space can be characterized or described by three numbers. The three numbers are values a, b, and c, such that a, b, and c are real numbers. This is what we call R3. So just like we had back in Calculus 1 and 2, we used R2, the set of all points in the plane, while here we can use R3 to describe the set of all points in three-dimensional space. So this is the three-dimensional rectangular coordinate system, and the idea is that every point in 3D space can be represented uniquely by a point, or by, maybe I should say, by a tuple. So a tuple or a three-tuple. So just a collection of three numbers in R3. And that's our three-dimensional rectangular coordinate system. We've now got a way to describe the position of any point using three values. Just a direct analog to how we worked in the coordinate plane, two-dimensional coordinate system. All right, let's get some familiarity with some objects in three-dimensional space. So which surface in R3 is represented by this equation? X equals 2. You might immediately think line, but that's because we're so used to thinking in two dimensions. Let's pause for a second and say, what is this thing trying to capture? Well, it's trying to capture the set of all points x, y, z in R3 such that the x component is 2. So in other words, this equation represents the set of all points 2, y, z, such that y and z are both real numbers. What is the set of all points where the x component is 2 and y and z could be anything? It might be easier to sketch this first. There's x, y, z. There's x equals 2. Let's say that's 2. So we'll draw a couple of line segments there. And now what I'm going to draw is essentially a plane. So there's a plane. And what is this plane? This plane is just consisting of all points where the x component is 2, y can be anything, and z can be anything. So this equation, x equals 2, describes a plane. So x equals 2 is a plane in R3. It was a line in R2, but now if we're thinking about it as an equation that's trying to describe the set of all points in space such that x is equal to 2, now that's a plane. So what's next? What is the surface in R3 that's represented by the equation y equals the square root of x? So again, let's get a sketch going on in here. So this is the set of all points x, y, z, such that x, y, z are real numbers and y has to be the square root of x, so positive square root of x. Or in other words, this is the set of all points x, root x, and z, such that x and z are in R. So knowing the x value forces me to take a certain y value, but the z value can be anything. So what is this going to look like? Well, I've got, it's kind of a funny way to draw this, but what I've really drawn here is I've taken the curve that I know in the plane, x, y, and y equals root x, and I've just drawn that curve now in the xy plane on our three-dimensional coordinate system. So the set of all points on that yellow curve satisfy this, and those are where satisfies the equation y equals root x, but the z value is 0. However, z's allowed to be anything we want, so we get lots of copies of this curve that sort of go all the way up. And so the idea is we got a whole bunch of copies of this same curve. And so we get this kind of surface that looks like that curve translated vertically up and down the z-axis. And this is known as a surface. In fact, it's a cylindrical surface. A cylindrical surface because every cross-section that I take, a horizontal cross-section of it, is the same. Now you may say it can be challenging to start to visualize this, especially since this is our first encounter with some three-dimensional objects. Is there a way to help you visualize this? And the answer is absolutely there is. There's a wonderful website, math3d.org. You can see the URL up there, math3d.org, put together by someone who actually does teach multivariable calculus and has incorporated a lot of the tools that are essential for us in this course in a nice, handy, easily accessible web page. So what I want to do is to sketch a few of these things that we just worked out. So when you first bring up math3d.org, this is what it looks like. It's got a nice sketch here of some surface, which we will explore in future sections. I'm just going to hit the cancel button on that. That's that X button you can see starting to get highlighted. If you hover over it and click X, that gets rid of it. Now we can insert a new object. The object I'm going to insert is something called an implicit surface. And what this allows me to do is write down an equation. So some stuff equal to some other stuff, and it will plot the set of all points that satisfy that equation. Our first equation was x was equal to 2. And there was that plane that we had drawn. So you can see the x-axis is coming out of the page essentially, the y-axis is going off to the right, the z-axis is going up, and we've got this plane right through x equals 2. You can click on the little gear icon next to the equation. You can drop its opacity down so you can maybe make it a little bit transparent so you can see through it. You can even change its color by clicking and holding on the color button there, change its color. Maybe we'll go yellow, and then I can click on it again, or click off of it, sorry, to get the color panel to go away. If I do a quick click on the color, it just turns the object from visible to invisible. And so there we go. Next, I will plot the other surface we just worked out. So this, again, implicit surface. We have y is equal to, we need square root of x, so I'll type it out, SQRT, converted it to a square root sign. We'll throw an x in there, and there we go. And we've got that square root function. And if I kind of look at it from the top-down view with x off to the right and y out to the side, kind of looks like that square root function, but now we've got, it's the set of all points that satisfy y is equal to square root of x, and z can be anything. So that's why that curve has been translated up the z-axis. And this is what we call a cylinder. It's not a circular cylinder like the one you're used to seeing. This is a cylinder made from the square root function. Other things you can do is you can add points. So for example, if I click a point button, and comes up with a default of 0, 0, 0. I can plot the point 1, 1, 1, for example. And you can see that this point actually lives on the surface. And you can check, and that's because the y component is the square root of the x component. 1 is the square root of 1. You can change the color of that point. You can also click the gear icon and change size, etc. If I made the x component -1, you can see now it's jumped to live on the other side of the YZ plane. It's now on the negative x side of the YZ plane. Alright, so that's just a recap of basically the things we've constructed so far in this course and a way to visualize them.